If you hit the mark, you must aim a little above it, for every arrow that flies feels the pull of the earth. Is the quote inspirational enough? Philosophical enough? What if I tell you it has got a bit of physics behind it as well? Let us see how. Suppose we have an India Pakistan cricket match at our hands. Our captain Virat Kohli is fielding at the boundary. Who wants to throw the ball to wicketkeeper MS Dhoni? Now, being the smart cricketer Virat Kohli is, he might want to know how fast and at what angle should he throw the ball so that it reaches Dhoni's gloves directly. He might also want to know how long will the ball take to reach Dhoni so that he has the best possible chance to get the batsman run out. Kohli might also be interested in knowing how high from the ground will the ball rise lest it hits one of the spider cams in the stadium. Now the answers to all of our captain's questions lie in a study of projectile motion. Let us now address the elephant in the room, friends, the projectile motion. If you take a ball and throw it in the air at an angle to the horizon, it will follow a path as shown. Now, any such path or any such motion under the influence of gravity is simply termed as a projectile motion. Now, before we tackle a problem, we need to know what the problem is. Hence, let us state our objectives for this video tutorial. We will try and find how far from the launch point will the projectile land or its range. We shall also try to calculate how high from the ground will the projectile reach or its maximum height. We are also interested in calculating for how long was the projectile airborne or its time of flight. The key to solving all these problems lies in one basic funda, which is to visualize any two-dimensional motion as separate motions on x-axis and y-axis respectively. To understand this, let us assume an object is moving along the path as shown. If we were to stand somewhere here holding a torch and direct the beam of light towards left, the shadow of the object will fall at this point on the y-axis, which will correspond to its y-coordinate. Similarly, if the torch was to lie somewhere here, the shadow will fall at this point on the x-axis, which will simply be its x-coordinate. Now we are going to extend the argument. Now, as the object moves with any velocity at any point on its path, its shadow here will move with the corresponding velocity along the x-axis, something we can call Vx. Similarly, its shadow on the y-axis will move with the velocity Vy. This very argument can be extended to object's acceleration as well. So what we have done through this entire exercise is that we've divided a two-dimensional motion into two separate motions, each with its own set of position, velocity and acceleration. Let us see how we can put this knowledge to use. This is the standard path for projectile here. You stand here again, flash a beam of light towards left. When the projectile is here at its launch point, its shadow will be somewhere here. And as the projectile moves from its launch point until up to its highest most point here, visualize it with me. Its shadow will rise vertically from this point until up to this point here. And as the projectile begins its downward journey from its highest most point to its impact point, the shadow will come down vertically along the same path to its launch point. In other words, the motion of shadow on y-axis is similar to the motion of a ball thrown vertically upwards under the influence of gravity. It will go up, stop at some point, and come back down along the same path. Now let us assume the projectile is launched with an initial velocity v along an angle theta to the horizon. The component of velocity along x-axis would simply be v cos theta, and the component of velocity along y-axis would be v sin theta. Now we are going to consider the motion of shadow on the y-axis. The shadow on the y-axis starts rising with an initial velocity v sin theta. as can be seen here. The positive sign here denotes its upward direction. And as the case would be with this ball here, the shadow will come back to its launch point with the same speed of v sine theta, but in downward direction. And since this vertical motion is under the influence of gravity only, the acceleration would be the acceleration due to gravity, which is always directed downwards. Now, if we use this equation of motion here, where Vf is the final velocity, Vi is the initial velocity, A stands for acceleration and T for time of flight, substitute these values and solve for T, we will get the time of flight of the projectile to be equal to 2v sine theta by g, where v is the launch speed, theta is the angle of projection, and g is acceleration due to gravity. To calculate the maximum height attained by the projectile, we will consider its motion from its launch point to the point where it attains its maximum height. As we know, when the projectile is at its highest point here, its corresponding shadow on the y-axis will also be at its highest point. And the velocity of shadow at its highest point would simply be 0. Also, the shadow started its upward rise with an initial velocity of v sine theta, while acceleration due to gravity acted upon it downwards. If we use this equation of motion, where Vf is the final velocity, Vi is the initial velocity, A stands for acceleration, and S is the displacement, substitute these values and solve for S, we will calculate the maximum height attained by the projectile to be equal to V square sine square theta upon 2g. We now calculate the range of the projectile, and as it's not very hard to visualize now, to calculate the range, we focus on the motion of shadow on the x-axis. You put a torch here and you'll observe that the shadow moves forward with a constant speed on the x-axis. In other words, in absence of any acceleration on the x-axis, the shadow has what we call a uniform straight line motion. And as is the case with any uniform straight line motion, distance is always equal to speed into time. Now the speed of the shadow on x-axis was always v cos theta. We had calculated the time of flight to be equal to 2v sine theta upon g. We substitute these values and later use the trigonometric identity. We'll find the range of the projectile to be equal to v square sine 2 theta upon g, where symbols have their usual meaning. Remember, we started a tutorial with what you needed to do to hit your mark with an arrow. I guess it won't be very hard to understand the physics aspect of it now. I hope this tutorial will help you aim right and hit the bullseye. Thank you so much.